So, rotational kinematics. Rotational kinematics is the description of rotational motion. Just like the regular kinematics, now we can call them translational kinematics, is describing translational motions, just moving without rotating. Or maybe the rotations are irrelevant, or maybe they're too small to see. Whatever it is, we've been describing motion without considering rotation much. So this is when we start describing rotational motion. And as you see, there's a lot of equations I have listed on the left side. And if you take a look here, we have constant acceleration motion, or we can call it a translational motion with constant acceleration. And we have how the position changes with time, how the velocity changes with time. And we also have rotational kinematics, which is constant angular acceleration rotational motion. We can see this is theta, this is the angle, how that depends on the initial angle theta 0, initial angular velocity omega 0, the time, and the angular acceleration time, and then how the angular velocity depends on initial angular velocity and also the angular acceleration and time. So these two sets of equations are very similar to each other, except that you take x, transcribe it into theta, takes v, transcribe it into omega, and you take a and transcribe it into alpha. So if you are already familiar with the constant acceleration motion or the translational motion with constant acceleration motion, you should be able to take all your knowledge over from there and apply your knowledge to the rotational equivalence. So let's get started with some comparisons. Since things are very similar, we'll start with a comparison, a set of variables. So we know x is position. So what is the corresponding rotational parameter? Theta. So that is the angle. And x is in meters. Theta is in radians. And the next variable is delta theta. Delta x, we call it displacement, also in meters. And it is defined as x2 minus x1. Right, so something that looks like this. So you have an axis, x1, x2, and well, this is delta x. Apparently it has a direction. Some object translates from x1 to x2 instead of the other way, so there has to be a direction. And what about the equivalence in rotational motion? That will be delta theta. So the angular displacement, that will be theta 2 minus theta 1. So an angle and a new angle, the difference between the two. So how do we do a drawing? Okay, we can still start with our axis, and we'll draw another axis. Let's say that this is theta 1. Alright, and this is theta 2. And the difference between the two is delta theta. And we're assuming that the angle goes from theta 1 to theta 2. So there's such an expectation that the angle goes this way. So there's already a direction, just like the displacement in translational motion. So so the next set of parameters to compare is velocity. So the average velocity, which is in meters per second. So that is defined as delta x over delta t. Right, it's in meters per second. And the corresponding rotational quantity is omega. So omega is angular velocity, average, so that's delta theta over delta t. And the unit, because theta is radians, this is radians per second. And then the next set will be the linear acceleration a. So a average is delta v over delta t. And the unit is meters per second squared. or meters per second per second. And then the angular acceleration alpha. So what that is if the angular velocity keeps changing with time, then you need an angular acceleration. So delta omega over delta t. And the unit is radians per second squared. Right. So these quantities are very comparable. That's why you see these equations are so similar to each other and one another. And we even have more things we can compare. These are a little bit beyond rotational kinematics, but it's good to keep the comparison going. For example, after kinematics, we learned forces, in linear motions, right? So forces are forces F, right? So in newtons, and in the rotational equivalence, we have tau. Tau is torque, and the unit is Newton meter. This is different from the unit of joule, which is also Newton meter. That Newton meter is sustaining a force in newtons, and the object moves for a displacement of meters. So that implies there's a duration of time in order for that displacement to happen. And this is not. This is sustaining force a certain distance away from an axis of rotation. So there's no implication that there's any duration of time that the torque has to be applied. So these are the two influences that would cause, for example, F is equal to mass acceleration, right? And tau, the torque, will be equal to, this is the rotational equivalence of mass, or rotational inertia, and angular acceleration compared to linear acceleration. So these two, angular mass and linear mass, right? Rotational inertia and the regular linear inertia. And we can keep doing the comparison. For example, we have, after we learned forces, we learned energy, right? So energy, I've listed them here. And now we can call this translational kinetic energy, 1/2 mass velocity squared. And the corresponding rotational kinetic energy, that is when something is spinning, and if it has this rotational inertia and is spinning at this angular velocity, it has 1/2 I omega squared in energy. So this looks exactly like that, right? Inertia and the corresponding velocity squared, inertia, corresponding velocity squared, and the 1/2 in both, right? So if you look here, these are slightly different units, but since these are both energies, right? They're both energies, so they're both in joules. If you look at this angular velocity, the unit angular velocity is radians per second. Radians is actually not a dimension; it's not a unit. So this is it's literally 1/second per second, right? This is just per second. And if you want the same unit, this side has kilogram, meters per second, and the square of that, so meter squared over second squared. And this thing has this thing's unit and per second squared. So what's missing is kilogram and meter squared. So that is the unit of rotational inertia, is kilogram meter squared. And after energy, we learn linear momentum, right? Linear momentum. Oh, by the way, we learned also the work done. Work done by a force is the force times the displacement, and work done by a torque is actually the rotation, the torque times the rotated angle, so angular displacement. And then after that, we learned linear momentum, which is m times v, and we'll also be learning angular momentum, which is I times omega, so inertia times velocity, inertia times velocity. So a lot of these quantities, they're very similar. The relationships are very comparable. So this should give you an advantage since you have learned everything about linear motion. You can take all those and properly map them to rotational motion. So just as an example of using rotational kinematics, let's calculate a turntable. So let's have an example. So we have a turntable that starts from rest and spins up to 3000 RPMs. In 15 seconds. So we have questions. What is the angular acceleration? And also, how much angle within the 15 seconds? So it's turning, right? So it takes 15 seconds to speed up. And how much angle has it turned during that 15 seconds? Alright, so let's have a list of parameters. We used to have lists of parameters like this: x0, right? X, v0, v, and a, t. Okay, so now we have an initial angle theta 0 and final angle theta, initial angular velocity omega 0, final angular velocity omega, angular acceleration alpha, and time t. So if the turntable starts from rest, and we can also assume that the initial angle can be called 0, and the angular velocity is 0 starting from rest, then we go up to 3000 RPMs. So let's put 300 here for readings per second. It's an approximate. We'll give some calculations on the side. And then the angular acceleration is unknown. The time is 15 seconds, right? So let's put some question marks here. That's an unknown. And this is an unknown, right? So we have two unknowns and the rest of them are knowns. And we also happen to have two equations. We know that routine, right? Two equations, two unknowns, we can solve them after we plug in the values. So why is the angular velocity 300 readings per second? So there must be a conversion between RPMs and readings per second. So let's do it on the side. Okay. So 1 RPM, that is 1 revolution per minute, right? So 1 rev per minute, if you multiply by 1 minute per 60 seconds, this is a 1, right? 1 minute is exactly 60 seconds. And then if you multiply by something else, 2 pi readings per revolution, or 1 revolution. Again, 2 pi readings is exactly equal to 1 revolution, right? So that's also effectively 1. So minutes, and revolution. So what we have is the 1 revolution per minute has been turned into 1 times 2 pi over 60 seconds, right? So 1 RPM equals 2 pi over 60 readings per second. So that's approximately 1/10, right? Readings per second. 2 pi is about 6, right? 6 over 60, that's roughly 1/10. So I'm using 300 as an approximate. I like the nice integer here. So now we have these numbers. We can use the formulas. So the final angle theta equals initial angle theta 0, initial velocity times time plus 1/2 acceleration and time squared. So we have 15 seconds, so there's a 0.5 times 15 squared is 225 alpha. And that's equation 1, the top equation. Then the bottom equation is omega is 300 equals initial omega starting from rest plus angular acceleration times time. So this gets us angular acceleration, which is equal to 300 over 15. So it's 20 readings per second. And we take that and plug it in here. The angle is 0.5 times 225 times 20. So 2.5 times 1/2, that's a 1. And then there's a 0, so the 10. Add a 0 there, so 2250. So 2250 readings of angle turned. And if you wish to turn this into revolutions, so 2250 over 2 pi, so that can give you a number of revolutions. So this is 358 revolutions. Thank you.